If you've studied economics, you've probably come across the concept of elasticity. But what does this mean exactly? Here's a definition. You can pause the video and read it if you like. And here's an example of a particular elasticity known as price elasticity of demand. As you can see, elasticity has to do with percentage changes in variables. But reading a definition does not bring a lot of clarity. So in this video, I want to provide some mathematical intuition for elasticity, and also discuss some topics that are often encountered in textbooks on economics. First, we need to understand the formula for percentage change. Here it is. The percentage change when the variable y changes from y1 to y2 is y2 minus y1 all divided by y1. That is the new value minus the old value all divided by the old value. Now I should mention that sometimes we scale up the formula by 100. But this will not be important for the treatment of elasticity, so I will ignore it. Here's an example yielding a value of 0.25, meaning that y increases by 25%. Now suppose we have two variables, d and p. We can think of P as the price of a good and D as the demand for that good on the market. The demand, of course, depends on the price, so that the change in the price results in a change in demand. Let's take the percentage change in demand and divide it by the percentage change in price. We then have a ratio of two percentage changes. In the numerator, we have the percentage change of demand, and in the denominator we have the percentage change of the price. We can rewrite this using delta notation. Here delta D means the change in D, that is delta D equals D2 minus D1. We then have the ratio of the initial values of price and demand multiplied by the ratio of the changes in demand and price. And this is in fact how we define elasticity of demand with respect to the price. So the elasticity is a ratio of percentage changes. Put differently, it's the percentage change of demand per unit of percentage change in price when we move from one point to another. Or, alternatively, it's the ratio of initial values multiplied by the ratio of the changes. Notice here that the elasticity of a variable is always defined with respect to some other variable, for example, demand with respect to price. To speak of the elasticity of a variable without specifying the other variable makes no sense. For completeness, here's the graphical interpretation. We have the price on the horizontal axis and the demand on the vertical axis. The demand curve slopes downward because demand decreases in the price. Here are the points, and based on the points we can easily find the changes. And having found both the points and the changes, we can set up the elasticity formula and calculate the elasticity when the market moves from the point P1D1 to the point P2D2. Now, in textbooks on economics, you occasionally find other definitions of elasticity. Some people use the absolute value of the changes. This implies that the elasticity is by definition always positive. Some people use the second point as a reference point rather than the first point. That is, they put P2D2 in the formula rather than P1D1. And some people use a linear combination of the 2 points. That is, they take a point on the demand curve somewhere between P1D1 and P2D2 and use that point as the reference point to put in the formula. You will find that all of these definitions are sometimes used. Now, having covered the basic intuition of elasticity, let's look at a numerical example using the numbers that you see on the screen. If we use the point P1D1 as a reference point, we get the value minus 0.83. If we use the point P2D2 as a reference point, we get the value minus 0.57. And if we use the midpoint as a reference, we get the value minus 0.69. Clearly, the value we obtain can vary quite a lot depending on which definition of elasticity we employ. Let's now look at how elasticity is calculated when we deal with continuous demand functions. This is how you will typically treat elasticity in economic theory. So we will assume that we have a demand function and that it's continuous. We differentiate the function and we obtain an expression containing the derivative of demand with respect to price. Next, divide by demand. We now have on the left-hand side the rate of percentage change of demand. That is, the differential of demand divided by the level of demand. Next, multiply the right-hand side by P divided by P and rearrange. Finally, divide by the percentage change of the price. On the left-hand side, we now have the rate of percentage change of demand divided by the rate of percentage change of price. But this, if you recall, is nothing else than the definition of elasticity. Hence, we find that for continuous functions, we can write elasticity as price divided by demand, all multiplied by the derivative of demand with respect to price. This is how you will usually see elasticity written in textbooks on economic theory. The last topic I want to cover in this video is the relationship between elasticity and logarithms. If you've studied econometrics, chances are you've come across this model. Here, the regressor is the logarithm of x, and the regressand is the logarithm of y. In other words, we regress the logarithm of x on the logarithm of y. Now, when both variables are given in terms of their logarithms, we say that the estimate beta1 is the elasticity of y with respect to x. But what is the justification for this? To see why this works, first take the differentials of the model. Then recall that the differential of the logarithm of y is equal to the differential of y divided by y. Combine these two expressions and divide by dx over x. Beta1 is in fact the ratio of the rate of percentage changes, or in other words, the elasticity of y with respect to x. I should mention though that since the data that you use in your regression is not continuous, this is only approximately true. That is, beta1 is an approximation of the elasticity, and the approximation can sometimes be quite far from the true value. In any case, there's one more thing to notice from this. Elasticity can also be thought of as the ratio of differentials of logarithms. This clarifies the connection between elasticity and logarithms.